Hey guys, we're going to record a little video here about the three basic types of motion so that you can be prepared for your homework. Now, before we do this, I want to make sure you understand the terms that we're using and also where you should be taking notes on this. All right. So if you are in regular physics, then it would be in this little table down here on the page about position, velocity, and acceleration. All right, now let's briefly redefine our terms. Position is represented by the letter X. It just represents where you are at some particular moment. Velocity is the rate of change in your position. Okay, so it represents how quickly your position is changing. Acceleration, represented by the letter A, is the rate of change in your velocity. So it's sort of two levels below, right? Acceleration shows how your velocity changes, and your velocity shows how quickly your position changes. All right, now, there's three, call them basic types of motion. So zero acceleration would mean, going back to this definition over here, that the rate of change in your velocity is zero. Okay. If the rate of change is zero, that's actually kind of just the same as saying that it's a constant value. So what that would mean is I'll start in this column, your velocity versus time graph would be flat. That sort of a graph, right? You've seen plenty of those before. So if the velocity versus time is a flat line, the position versus time would be something like that. In words, what we would say is that it is linear. Okay, now the idea here is that if your velocity doesn't change, your velocity has a constant value, then your position changes at a constant rate. That's what a line shows, right? A line goes, over 1 up 2, over 1 up 2, or, whatever it may happen to be, depending on the slope, okay? Which is showing then that your position changes at a constant rate over time. Okay, moving on down. If you have positive acceleration, then your velocity versus time graph would show a positive slope. That's what positive acceleration means, is that your velocity is becoming more and more positive, okay? So you've got a positive slope on it. So it could look something like that. Although there's no reason why the velocity has to start at 0, okay? This could also work. If it's positive acceleration, then your velocity graph will have a positive slope. All right, the position versus time graph. If you can't quite tell because of the resolution of the video, that is half of a concave up parabola. So what we are saying here is the following. If you have positive acceleration, then your velocity is becoming increasingly positive. Okay? So if you're starting from rest, that means, after, say, 1 second, you're going at 3 meters per second. And then after 2 seconds, you're going at, say, 6 meters per second. And then 9, 12. So as each second goes by, the rate at which your position changes is growing. You're moving faster and faster, and therefore your position is changing more and more quickly. That is what a parabola shows you. At first, it's not very steep, which means you're not going very fast. Your position is changing more gradually, right? But as time goes by and that slope increases and you're going faster and faster, your position is changing more and more rapidly. The slope of this graph tells you the velocity. The slope of a position graph tells you the velocity. So that means that if your velocity is increasing, then your slope should also be increasing. And that is exactly what we see here. Okay. All right. Negative acceleration. Your velocity versus time graph will have a negative slope. the classic example that we will use for this would be that of throwing an object up into the air. So if you throw it up into the air, as we've discussed, the initial velocity would be positive. Okay, all right, because you threw it up in the air, so positive initial velocity, right? As it moves upwards, because gravity is dragging it down, the velocity would decrease. And so what you would see here would be a negative slope on your velocity versus time graph. Okay, so if it's something like this, right, what you would see on your position versus time graph would be a concave down parabola. All right, now just for simplicity, for right now, let's not worry about this other half of the graph. We'll get into that when we do a later example, okay? If this is what your velocity versus time graph looked like, because it was something like, I don't know, let's say you are slowing down your car and coming to a stop, all right? What that would look like on your position versus time graph would be, well, initially you're going faster, right, fast, okay? And as time goes on, you're slowing down. The slope of the position versus time graph is your velocity. So if initially you're going fast, then that would be steep. Okay, but over time, your velocity is less and less, which means this graph should get less and less steep as you go along. So it would look like a concave down parabola, just like I said. And if at the end of this time all you do is stop, then this would, level off and stay at that particular height and not do anything else after that. All right, now we're going to try a few examples that are going to use these shapes of graphs here, and that will help get you ready for some of the homework problems. And they're going to come from example 7, which is, if you're in regular physics, at the back of your packet, okay? So it should start off with, a car moves with a constant velocity down the highway. Okay, all right. So what we're going to do then is we're going to draw position, velocity, and also an acceleration graph for each of these. The acceleration graph, by the way, should pretty much either be like a flat line or a different flat line. Okay, it should show like one constant value, whether that be a positive number, a negative number, or 0, unless the acceleration is changing partway through motion. Okay, let's give that a try. So what you should try and do then is take what you learned here and pause the video and try and figure out what your graph for part A should look like, and then resume the video. All right, now in part A, it says the car is moving with a constant velocity down the highway. Okay, constant velocity is another way of saying 0 acceleration. Okay, so we've got a couple of vocabulary terms that mean the same thing, all right? If I say, and you should write this down somewhere, please write this down. If I say that I have a constant velocity or 0 acceleration, those mean exactly the same thing. Okay, so our graph for acceleration versus time is going to be a flat line at 0. That's it. All right, my velocity versus time graph. It says it's a constant velocity. Okay, so that should be also a flat line. All right, whereas my position versus time graph should be showing the position changing at a constant rate. Okay, so that is exactly the graph that we drew before. All right, go ahead and pause, try example B. All right, for the next one, it says that the ball is rolling down the incline, and we're supposed to call down negative. Okay, so if we're doing that, the acceleration should be a constant negative value. So there's my acceleration versus time graph. My velocity versus time graph. All right, if it's rolling down the incline and down is negative, and it has a constant negative acceleration, that means it should be going faster and faster, which would be represented like that. Okay, that being the case, we should know if we have a negative acceleration, we should have a concave down position versus time graph. And based on this, it should be going faster and faster in the negative direction. And so my graph should look like that. It will be going faster and faster in the negative direction. All right, part C is actually kind of similar to this one, except that the ball starts off moving up the ramp. All right, this one is maybe the trickiest. Okay, so give it a think, all right, and then resume the video when you think you've got it. All right, so the first thing that people usually mess up is the acceleration. They're like, well, so it was rolled up the ramp, and so that, no, hold on. All right, ignore the push, all right? We're only looking at after your hand has left it, okay? So it's rolling, just rolling up the ramp and then rolling back down the ramp. Well, the acceleration for the ball on the ramp, whether it's moving up or stopped for an instant or rolling back down, the acceleration is this way. The whole time, the acceleration is down the ramp. So don't change what you did from part B. Your acceleration graph should be exactly that. The direction that it happens to be moving is velocity. That's not the same as the direction in which it is accelerating. All right, now my velocity versus time graph, well, I've given it a nudge up the ramp. So the initial velocity should be up here. It has a negative acceleration. So that means this should be going down, okay, until it reaches the top of its motion, wherever that is, where, of course, it will come to rest for an instant, as we should be familiar. All right, now the tricky bit is after that. A lot of people want to do this. That's not actually quite correct. So the correct way of drawing this would actually be for it to continue on down like that. All right, now if you're wondering why would that be? Because like it goes up, so I get slowing down, and then it speeds up after that. So shouldn't it do, hang on now. This is a velocity versus time graph. This graph that I first drew would be showing it rolls up the incline, stops for an instant, right? Slows down, stops for an instant, and then continues rolling up the incline, but faster and faster. All right, that's nonsense. That's absolutely not what happens, right? We all know that what it does is it rolls back down the incline faster and faster. Remember, please, signs indicate direction. So if it's got a negative velocity after this moment, then it should be going in the negative part of your graph. All right, now my position versus time graph will be a full concave down parabola, which should make sense, but let's just make sure that it jives with everything, right? It initially is moving upwards, fast. It slows down, so this graph gets less steep. At the very top, you can see it's flat because it stops for an instant. And then, after that, it's rolling down the incline and faster, thus more and more steeply. The only sort of extra wrinkle that's added into the homework is, remember, things can do two things, okay? You could have someone who is driving along at a constant speed for a while who then applies the brakes. Okay, so if it's something like that, then your graph may in fact be a synthesis of two things. So in other words, it could look like, for example, this and then that, right? So where it's leveling off, all right? Or maybe it goes concave up for a while and then linear after that moment. That would be two types of motion in one, okay? Now, it's just application of this example, okay, but try and see what you can do with that. All right? Thanks, guys. Hope that helps.